So we're going to continue to measures of variability. So before we're doing measures of location, remember, like I said before, we're doing this for ungrouped. We're doing this for ungrouped. And unweighted data. So you're going to have slightly different formulae for grouped and weighted data. So variability basically is going to measure how how variable the data is, how much variance you have in the data. So the first thing you're going to have is the range. The range is simple. It's simply the highest value minus the smallest value. So that's it's one of the most straightforward measures. Range for our data is going to be range. Do we have a range function here? Actually, we don't. Yeah, but it's really easy, because once you've already sorted your data, all you have to do is to get the last index. In this case, it's going to be 21 minus the first index, which is 1. So the other thing we can also, the other range we can compute is the interquartile range. This is the difference between Q3 and Q2. It's the difference between Q3, sorry, and Q1. So that's going to be the so in this case, our data is ranging from A2 to A21, and we want to go Q3 minus Q1, and our data, like I say, is ranging from QA2 to A21, and we want Q1. So to give us the interquartile range. Then the other thing that we might be interested in is the variance. So the variance, there's two slightly different formulae that you can compute. First of all, you can do what you call the sample variance. So let's just do the sample variance. Let me start a new equation. I need a new symbol. So I'll go with this. So the sample variance is actually going to be the you're going to have the summation it's going to be the summation from I is equal to 1 to I is equal to n. You want to sum over the sum of the different so you want to get the sum of all the different deviations. You want to get the sum of all of the different deviations. So you have some x x of I minus your minus your x bar, or the mean. So you want to get all these different. So for the sample standard deviation, you want to get, oh wait, this is going to be you also want to square this, yeah. So for the sample standard deviation, you're going to have the square deviations for the summation of the square deviations over n over 1. N minus 1 rather, where n is the number of elements that you have in your data. So this is I should write it properly. So this is the sample variance rather, not the standard deviation. So this is the sample variance. Then you have the, then you could also have the population. You can have the population variance. So when you have the population variance, normally we use sigma for this. Do I have sigma? Yeah, you use sigma for this. It is actually over, simply over n. This is the population variance, and that is the sample variance. So we can do this step by step. So let's see, maybe let me just get rid of these measures I had before. So this is basically, this is our x, right? Then we want to have the mean. In this case, our mean is going to be summation over, so from A2, actually we have B2 to B21. Column A is actually the indexes. So over the count, B2. So I'm writing in the actual formula to B21. I could also just use the Excel function, which is average, and that's going to be B2. We put in the range to B21. Still gives us the same value, and then we are going to have the deviations now, the x minus x bar, x minus x bar. So that is going to be, it's going to be this value minus the mean, and the mean is going to be in cell B23. I just have to fix it so the formula doesn't keep changing. B2 minus B, oh sorry, it should be B24. B23 is the, sorry, I mean C23. So just bear with me for a bit. So it's actually C23. So yeah, so we have this. So we have to square this. What we want is the magnitude of the distance from the mean. If we leave in the sign, then so we do this so that we can get rid of the sign, right? So it's going to be whatever that is by itself. So the square of that. So here we go. So then we are. So next we want to get the summation, yeah. So the sum of the deviations is going to be sum of D2 to D22. So then the variance, sample variance, is going to be this, the sum of the deviations divided by the sum of the square deviations divided by the number of values that we have, which is going to be B2 to B21 minus 1, and I want to make sure all that is, so that is our sample variance. We could use the function to just confirm. So this is var s B2 to B21. Do we get the same value? Sample variance, sum of the deviations. So this the deviation should be, okay, it should go up to 22. C25, so this should go up to 22. C25 should be the sum of D2 to D22. C25, and the mean should be all the way to 22. And then the mean should be 2 to 22, so the mean should be all the way to B2 to B22. Then the sum of the deviations should be sample variance should be C25, the sum of the deviations. The sum of the deviations is D2 to D22, and count B2 to B22. So I'm not sure why I do not get the correct value. It's close, but there's a problem. So this is the, okay, this should be to B22. Yeah, so you get exactly the same value if you use the function. Then you could do the population variance. Population variance. So the population variance is going to be the sum of these devs, sum of these deviations, over the over count B2 to B22. Gives you that value. So in general, you should have a lower population variance than a sample variance, because the denominator and the population variance is going to be smaller by 1. So this is a var p B2 to B22. So here we go. So you get exactly the same value. So that is just proof that you are using the correct formula. Then you could do the standard deviation. Let's do the population standard deviation is going to be the square root. It's going to be square root of that, yeah, of the population. Then the sample standard deviation is going to be the square root of the sample variance, right? Alternatively, you could use the standard deviation function stdev_p for population standard deviation B2 to B2 to B22. So you get the same value exactly. So then you could get the standard deviation for the sample standard deviation function, which is going to be B2 to B22. So that gives you the exactly the same value here and there. Then, so this is a standard deviation and the variance. So S. So that's why we denote this as sigma squared, because the standard deviation is sigma, the population standard deviation is sigma, and that is S squared because the sample standard deviation is S. Then you can look at the coefficient of variation. So the coefficient of variation is the standard deviation divided by the mean. I'd use this to compare different ranges. If you had two, for instance. So these values are, let me just create a new sheet. So if you had two values, two groups of values, for instance, here you have heights of dogs, and then here you have heights of people. Yeah, heights of people. So you're going to find that dogs are basically shorter than people. Yeah, so you're going to find that, for instance, it would be some random value. The height of a dog could be some random value between 2 and 4. It is a random value between 2 and 4. Let me be more generous. Maybe you have but you can't have more than. Let me say you have some Great Danes in there. So some of your dogs are all the way to 5 feet. So let me say you have about 30 dogs. Then you have heights of people. And the height of a person could be anything between, of an adult person, could be anything between, let's say, 4 feet and 7 feet. Yeah. So let's see what happens now. You have this. So if you compare, if you look at the means of this data, mean height of dogs, is going to be the average of column of the values in column A2. So that is of A in column A. So A to A 31. If you get the mean height of people, because the values are bigger, so you expect mean height of people. So you expect the average height here to be higher, right? Simply because people are higher, are taller than dogs, to be 31, right? So you have the average of 5.6. If you look at now the variance, let me look at the standard deviation for dogs. Let's look at the sample standard deviation. Let me fix this value so they stop, they stop flipping each time I make a change. So let me just copy and repaste. So now they are fixed as values. So let's see the standard deviation of dogs. Sample standard deviation is going to be std dev s, and dogs go from A2 to A31. Then the sample standard deviation people is going to be std dev. I want the sample standard deviation B2 to be 31. So you can see that the standard deviation for people is actually higher, right? But that is purely because you have higher values for people, right? So if you want to compare these two, if you want to compare the variability, then you can normalize by the mean. So if you normalize by the mean to get the coefficient of variance, you're going to find the coefficient so the coefficient of variance for dogs is going to be the sample standard deviation for dogs divided by the mean for dogs, and then the coefficient of variance for people is going to be the sample standard deviation for people divided by the mean for people. So you find that these are, they are not so far apart. Let me just go be sure average B2 to B31, A2 to A31, B2 to B30. So if you want to compare these two and the means are different, this is how you standardize. So obviously we still have more variance in people. So this could be because, let me see, how many values do we have here? So this was run between 4 and let me just make sure you have the same range. This was 4 and 7. This was run between, so 4 and 7, you have 4, 5, you have 4 values, right? Let me just increase this to run that you have the same number of values rand between so dogs were ranging from 2, so that was 4 to 7, so let's have 2 to 5. Let me just copy, let me just paste. So this is 2, this is 4 and 7, 2 and 5. Coefficient of variance. Now you actually see that we have a higher variance, a higher coefficient of variance for dogs, but for people, we have a higher standard deviation. Do we? I have to be sure. So mean height is 3.7, mean height is 5.3. So this is 4 to 7. We still have the same kind of data. Coefficient of variance be D32 or divide by D33 divided by B33. Yeah, so we have this kind of situation where you actually have more variance in the dog population. So this allows us to compare the two. Actually, I forget, we have to multiply this by 100. It is given in terms of percentages. So sometimes you can have a higher variance. Not sometimes. A lot of the time you can have a higher variance between different units, simply because one range is way higher. Yeah, simply because one range is way higher. And if you want to correct for that effect, then you use the coefficient of variance. And then the other thing that we can look at is skewness. There's a formula for skewness. So skewness, I've already told you before that this is this data over here is going to be left skewed. In other words, the frequency density is higher on the right. Then this is this is right skewed because the frequency density is higher on the left. And this kind of if it's right skewed, you have a positive skewness. There's actually a formula for skewness. So the skewness is going to be, it's given by this formula. Well, let me just use that. You don't really need to know this formula, but I'm going to just provide it. It's actually 1 over n minus 1, n minus 1 into n minus 2 into the summation from I is equal to 1 to I is equal to n into the cube of the sum of the deviations. Into the cube of the sum of the deviations. There's another fraction here. So there's actually going to be another fraction here, to the cube of the sum of the deviations. I'm going to use mu for the mean over the sample standard deviation. So this value over here actually is what you refer to as a z-score. This x minus mu over the sample standard deviation. So let me just talk about the z-score. So the z-score, I've already told you, is this value here. x minus mu over the sample standard deviation. I thought I copied it. So so you don't really need to know this formula, but if you wanted to know where you get these values from for the skewness, oh, I still don't get it. Okay, let me just write it again here. So we said the z-score for any value is going to be is essentially the distance of that value. I don't want the uppercase x, so it's going to be the distance of that value from the mean, which I'm going to write as mu, right? Expressed in terms of standard deviations. So this is the z-score, right? So if I wanted to get for the z-score, you actually use the sample standard deviation. So if I wanted to get the z-score for this value, for instance, it's going to be, so the z-score it's going to be that value minus the mean, and the mean for these values is B33. So let me just fix it, and then this is going to be over, so remember there's board mass, so if you want to make sure you get the right value, you have to enforce the order of brackets. So this is going to be divided by the sample standard deviation, which is that, then D33, so I should get something like this. Yeah, so generally your z-scores should not be, it's very rare to get z-scores which are greater than 3 in data. I'll tell you why in a bit. So this is the z-score, yeah. So which is simply x minus mu okay, so that brings us to the end of that video.